Okay, get this. What if I told you that there's an invisible force? A force that powers pretty much everything that moves in our modern world. I'm talking about the silent hum of an electric car, the vibration in your phone, you name it. It all boils down to one simple but seriously powerful principle. Today, we're going to uncover what's called the motor effect.
All right, so let's just start with a basic question to get our heads around this. I want you to imagine you've got a really strong magnet, right? It's creating a magnetic field. Now, what do you think happens if we stick a wire right in the middle of that field and then zap, we pass some electricity through it?
You might not expect it, but the answer is it moves. Seriously, an invisible force just kind of appears out of nowhere and shoves the wire. It's wild. This is the core phenomenon we're going to unravel today. And yeah, you guessed it, it's called the motor effect.
Okay, so to really get how this works, we need to look at the two key ingredients here. Let's break down what's actually happening on the scene.
So clue number one is the magnetic field itself. Pretty straightforward, right? You've got a north pole on one side and a south pole on the other. And between them, you get these nice, neat, parallel lines of force. Think of this as our stage, a perfectly uniform magnetic field just waiting for something to happen. All right, now for clue number two. And listen up, because this is absolutely crucial. The moment we send an electric current through that wire, bam, the wire itself becomes a magnet. It creates its very own magnetic field, a circular one that wraps all the way around it. Okay, so let's put it all together. We've got the straight field lines from our big magnet, and we've got the circular field lines spinning around our wire. So what happens when these two totally different magnetic fields meet? When they're forced to share the exact same space? Well, that interaction, that's the aha moment. This is where the magic really happens. It's how that mysterious force is born. Let's zoom in and see exactly how it works. Right, check this out. On one side of the wire, the fields are basically moving in the same direction. So they team up, they add together, and you get this stronger, more squished together magnetic field. But on the other side of the wire, they're pointing in opposite directions. They basically fight each other and cancel out, leaving a much, much weaker field. So here's the bottom line. The wire is now stuck between a really strong, high-pressure field area on one side and a weak, low-pressure area on the other. And what happens when you've got high pressure next to low pressure? You get a push. The wire is literally shoved from the strong side to the weak side. And that's it. It moves. And that, my friends, gives us our official textbook definition of the motor effect. Whenever a conductor carrying a current is placed inside a magnetic field, those two fields are going to interact, and that exerts a force on the conductor. You'll want to burn that phrase into your brain. It's the key takeaway. Okay, so we know there's a force. Great. But which way is the wire going to move? Up, down, left, right? Well, thankfully, we don't have to guess. We have this awesome tool. You can think of it like a secret decoder for physics. It's called Fleming's left-hand rule. All right, seriously. I want you to do this with me right now. Hold up your left hand. No, not your right, your left hand. Okay? Now, point your first finger straight out. Got it? That represents the F field. Now, stick your second finger out to the side, making an L shape. That's your current. Now look at your thumb. It's pointing straight up, right? That is the direction of the force, or the motion. And here's a super easy way to remember which finger is which. Your thumb, well, that's the force or the motion. Your first finger is for the field, and your second finger is for the current. So you just line up what you know, the field and the current, and your thumb will magically point in the direction of the force. Works every single time.
So a little push on a wire is cool and all, but how do we turn that into something actually useful, like, say, a spinning motor that can power a car? Let's take a look at how this one little principle gets scaled up to become one of the most important inventions in human history.
Okay, so instead of just one single wire, in a motor, we use a whole coil of wire, usually a rectangular loop. And pay attention to this part. The current flows in on one side, goes all the way around the loop, and then flows back out the other side. This is key because it means the current is traveling in opposite directions on the two long sides of that coil. Now let's get our left hand out again. If you apply the rule to each side, you find something absolutely brilliant. Because the currents are opposite, the forces are opposite too. One side of the coil gets pushed up, and the other side gets pushed down. And what happens when you push up on one side and down on the other? You get a turning effect. The coil starts to spin. But wait, there's a problem.
After the coil spins halfway around, the forces would flip, and the whole thing would just stop and wobble back and forth. So, how do we fix that? With a truly genius little invention called a split ring commutator. It's basically a metal ring that's been split in half. Its only job is to cleverly reverse the direction of the current every single half turn. This keeps the forces always pushing the coil in the same direction, giving us that continuous spin we need.
So, what if you want a stronger motor, a more powerful one? Well, it's actually pretty simple. You've got three main options. You can crank up the electric current, you can use bigger, stronger magnets, or you can just add way more loops of wire to your coil. You boost any of those three things, and you're going to get a bigger turning force. Simple as that.
All right, you knew it was coming. This is physics, after all, so there has to be an equation to tie this all together, right? Let's take a look at how we can actually calculate the exact size of the force we're dealing with. And you're going to love this. The equation is incredibly simple. It's just force equals B times I times L. So F is our force, which we measure in newtons. B stands for the magnetic field strength. Its official name is magnetic flux density, and we measure that in Tesla. I is the current in amps, and L is simply the length of the wire that's actually in the magnetic field, measured in meters. So just remember, F equals BIL. Easy. And what's really cool about that equation is how direct the relationship is. The force is directly proportional to all three of those things. What does that mean? It means if you double the strength of your magnet, guess what? You double the force. If you triple the current, you triple the force. It's a perfect one-to-one relationship, super predictable.
So let's just run through a quick example to see it in action. Say our magnetic field is 0.2 Tesla. We're putting 3 amps of current through it, and we've got 0.05 meters of wire sitting in the field. We just plug it in and multiply. So 0.2 times 3 times 0.05, and that gives us a force of 0.03 newtons. See? Simple as that.
So think about that. We went from a simple twitching wire all the way to this fundamental principle that literally drives our modern world. This one single effect is the secret behind electric cars, blenders, washing machines, fans. I mean, the list goes on and on. It's incredible. So the only real question left is, now that we all understand how it works, what are we going to build with it next?